Good time of the day to everyone from Seattle. In my presentation, I will talk about non-contact photoacoustic diagnostics and its application in lab medicine. Non-contact optical detection of ultrasound vibrations in most cases rely on optical interferometry. In interferometry, a sample and reference arms form an interference signal with intensity modulations proportional to ultrasound displacement. Unfortunately, this method works well only for polished, highly reflecting surfaces under quiet laboratory conditions. If we consider this method for industrial or clinical applications, this is not the case. Indeed, any noise vibrations applied to a mirror will immediately appear in the ultrasound signal. In addition, skin or any other tissues produce scattering. It means that the speckles in the reflected beam can totally destroy the interference signal. In 2013, we developed a fiber optic Sagnac interferometer having a very different operation principle. It looks like a bunch of fibers, and it is. In our design, we propose to split interfering beams in time rather than splitting them in space. It means that there is no reference arm in our design, and both beams are reflected from the same point of the surface. The main advantage is, again, there is no reference arm. It means that it's extremely stable to environmental noise with no stabilization required. It's much sensitive to surface roughness because, again, two beams are reflected from the same sample point and nearly insensitive to speckles. There are many other advantages of its design, including that the bandwidth of the detection can be adjusted by the fiber length in the range from 100 kHz to GHz for the same detector. So you don't need to change the detector to change the bandwidth. Our approach has been extensively tested in industrial NDT. This funny movie shows what can happen with an airplane, and it's not clear what to do next, especially if an airplane is made of composite materials. Note that the rate of accidental collisions on average is 1 a year per every airplane. We developed a fully non-contact system to inspect aircraft composites. Here is an old implementation from 2013. We can see very fast scanning with online laser ultrasound inspection with no contact to a sample. Now the system is fully installed on a robotic arm in the Boeing facility. We can see pretty much everything in aircraft composites, for example, input damage with quality and resolution, better in micro CT, or we can visualize individual pores in composite structure. In our non-contact fiber optic detector, we use only 30 milliwatt power, which can be used even for clinical ophthalmic applications. In literature, you can find lots of studies comparing non-contact to contact detectors, but most of them were not done apples to apples. An ultimate sensitivity of the detector, independent of its nature, optical, contact, or electrical, should be compared with a Johnson-Nyquist thermal noise, which is defined by molecular thermal motion, so it's internal noise of the object under study which cannot be overcome. The measured noise power of a Sagnac detector is only 6 times worse, so it's really hard to make the detector better. Having such a comprehensive NDT background, we solve a couple of interesting and important biomedical problems. For example, UV spectrophotometry is a conventional lab tool which is presented in most biomedical labs. If we measure a spectrum of molecular absorber, which is here, there is no issues. But if we add inhomogenities into a solution, for example, nanoparticles, cells, tissues, the spectrophotometry fails because of light scattering. A simple demonstration is only right. We use cupric sulfate solution with different concentration of microspheres. As seen, the UV spectrum of the mixture, blue curve, is not equivalent to the sum of component spectra, gray and black. and only photoacoustic method measures the correct spectrum. The proposed photoacoustic method was also shown to be insensitive to light scattering in the solution and always produces the correct absorption even at very, very high scattering. Another example is related to gold nanorods. This figure shows that if you measure the GNR UV spectrum, black curve, it doesn't correspond to the true light absorption, blue curve, due to intrinsic light scattering of nanorods. Actually, most nanoparticles scatter light in addition to absorption, and you face a similar situation. And only the photoacoustic method measures it correctly. A more complicated situation is when GNR is mixed with cells, but not internalized within cells. The spectrum, the dark green curve, is very inaccurate, but the photoacoustic method works out again. And finally, when GNR were internalized within cells, the conventional spectrophotometry shows absolutely wrong spectrum by both shape and magnitude. You can find this incorrect spectra in thousands of papers. Unfortunately, most people still rely on conventional spectrophotometry. We believe that non-contact spectrophotometry can dramatically improve capabilities of the conventional UV-VIS method. And finally, can we make it work in vivo? If we calculate a thermal noise pressure for a 10 micrometers optical spot, we will get about 2 kilopascals versus a few pascal, which a 6 millimeter aperture focused piezoelectric transducer can provide due to a much larger aperture. The main problem in photoacoustics is low signals, unfortunately, and with optics, we reduce detection sensitivity by 2 to 3 orders of magnitude. A non-contact optical array has not been demonstrated or even outlined yet. Pressure scanning can be done, but it's much slower than modern OCT systems. I really don't think that the contact is a problem for clinical imaging. Burns maybe, but vascularization at burns can be imaged with OCT angiography. Although non-contact photoacoustic detection can be a great tool for lab medicine applications, I'm quite skeptical about in vivo non-contact photoacoustic imaging.